All right, so in this continuation of chapter 2, we are going to look at a number of things. We are going to continue talking about an atom. We will look at briefly look at the modern atomic theory, and then the subatomic particles, the particles that are found inside an atom. Then we will talk about atomic numbers, atomic masses, and then we will end with isotopes and the calculations that are involved with isotopes. So, in terms of the modern view of an atom, the theory that we have is that we have an atom, the atom that has protons. So we'll see what protons are in the coming slide. But protons are positively charged. They are positively charged, and they are found in the nucleus. Then we have neutrons. Neutrons have no charge. They are also found in the nucleus of an atom. Then we have electrons. Electrons are negatively charged, and they are found in what we call energy levels or electron shells. So the modern view of an atom is that an atom has two parts. The inner core of an atom is the nucleus, and then the nucleus is surrounded by energy levels or what we call electron shells. So let me now to describe electron shells, we use what we call a cloud theory. Of an atom. So in this case, we say that the electrons are found in specific clouds. So you can see that here, we see that there is a cloud here, and within this cloud, we have electrons. Like we have this electron here within the cloud, this electron here within the cloud, this electron here within the cloud. So this is where you find electrons. There is no specific location you can find these electrons, but there is a probability. So a high probability of finding an electron within these electron clouds. So about 95% or 90%, that's not the focus now. And we are going to learn more about these clouds when we talk about modern view of an atom, but in a detailed form. So these clouds, we call them orbitals, but we are going to talk more about orbitals later. One important thing to take note of is that in these clouds, we just have a probability of finding an electron. We are not 100% sure that the electron is there, but we have a probability, maybe about 95% probability of finding an electron within the electron clouds. Now, the difference between these two diagrams, let's say diagram A, diagram B. In diagram B, I can see specifically where the electron is. I know that there's this line here. Maybe I call it an orbit. There's this line here, and the electron is within this line here, or this circle. So there's a second circle here, and the electron is also within this circle. So I can easily point out the electron there. But when you look at the electron cloud here, you really are not 100% sure where the electron is, because the electron can be anywhere within the cloud. You can see the electron here, you can see the electron here, you can see the electron here, you can see an electron here. So that's the difference between the line theory, or between these circles in B and the clouds in A. Now, just to make matters easy, when presenting electrons, so let me write the diagrams again. To make matters easy, when presenting electrons, we use this diagram. Or when presenting an atom, we normally use diagram B. Although we know that it has limitations, it does not show us the clouds. But we usually use diagram B because it is simple and we can easily follow where the electrons are. Although in actual sense, you don't know exactly where the electrons are in an atom. So really, when you look in your book, and later on in this class, we'll be focusing on an atom using diagram B. Now, let's try to look at these particles inside an atom. So we say we have nucleus, which is the core, and then we have energy levels, that are the electron clouds. So these clouds are surrounding the nucleus. Now the nucleus has two particles in it. So the nucleus has protons and neutrons. That's what the nucleus has. The energy levels have electrons. So these energy levels have electrons. So what are these particles? So an electron has a charge of -1, shown here, and has a mass in grams of 9.01 times 10 to the power 28. This mass is translated to 0.0005 atomic mass unit, and we'll see what an atomic mass unit is. A proton has a mass of 1.673 times 10 to the negative 24, which is translated as 1.007 atomic mass unit. And you can see the charge of a proton is a +1. A neutron has similar mass to a proton with only a slight difference. So you can see here, a neutron is also 1 atomic mass unit, but the neutron is not charged. So a neutron has no charge. Now, if we look at the masses of electrons and protons, we can see that the electron really has a very small mass, which is almost negligible. But the mass is there, yet it is negligible. So really, when talking about an atom in terms of mass, we use these two. We use protons and neutrons. However, if you want to talk about an atom in terms of charge, then you use these two, electrons and neutrons. So that is a simple description of the subatomic particles. So subatomic particles are just particles inside an atom. Now let's move on. So sometimes I am going to ask you to present an atom in terms of a symbol, and also to take note that an atom is an element. So it has an element symbol. Then it has what we call a mass number that we are going to define, and then what we call the atomic number. Previously, I said that when you want to talk about mass of an atom, you need to focus on neutrons and protons, or protons and neutrons. So by definition, mass number is the number of protons plus number of neutrons. So when you add the two, you get a mass number. Atomic number. Atomic number is the number of protons. Atomic number is important because it gives the identity of an atom. So the atomic number gives the identity to an atom. So for example, if an atom has 6 protons, you know that that atom has an atomic number of 6. Therefore, the atom is carbon. If an atom has 7 protons, you know that the atom has the atomic number of 7. and therefore that atom is nitrogen. So the atomic number is the identity of an atom. If you change the atomic number, you have changed the atom altogether. One other important information: in a neutral atom, number of protons is equal to number of electrons. So if you are told that this atom is neutral, and you are given a symbol like this one, and here you have an atomic number of 11, which means 11 protons, that will tell you also that you have 11 electrons based on this statement. So you need to write down this information. So let me take it off. Now, the symbol that we are showing here, the way we write, we are showing here in a generic form is given as shown here. So we have an AZX symbol. So X, A, and Z. This one, the X, is element symbol. A is the mass number, and Z is the atomic number. So I'll be asking you to draw an AZX of a specific atom or something like that. Let's move on. So as I already indicated, when you look at an atomic number, it's just number of protons, just number of protons. Identity of atom. Mass number, number of protons, plus number of neutrons. Now let's see how we can use information from, I'll just write here, A, Z, X diagram to determine what we are dealing with. So consider the following atom. So the atom is given as 75, 33X. So as shown here, determine the number of electrons, protons, and neutrons. So first, I'll write this down and say 75, 33, and I'll know that this is my mass number, which is number of protons plus number of neutrons. And then this is my atomic number, which is number of protons. Now, once I do that, I come back here and say, how many protons do I have? Based on this information, I know I have 33 protons. What about electrons? I also have 33 electrons because I know that in a neutral atom, the number of protons is equal to the number of electrons. What about neutrons? So the number of neutrons is the mass number times the number of protons. So it's mass number, not times, minus. Mass number minus atomic number in this case, which is 75 minus 33, giving us 42 neutrons. So that's how we solve a problem like this one. Let us go on to look at another problem. So I'll get rid of all the ink. I hope you have written it down. So here the protons, I'll just say 33 electrons, 33 neutrons, 42. So let's look at this next question. So draw a diagram for an atom of carbon which has 6 electrons and a mass number of 12. So we know that the symbol for this is C. That is our symbol. And this carbon has a mass number of 12. But do we know the atomic number? Yes, we know. Because the number of electrons is equal to the number of protons. So if the number of electrons is 6, it means the atomic number is also 6. So that is the AZX symbol for carbon. So let's just look at something. Now, in the previous slide, we talked about atomic mass unit. So what is this atomic mass unit? The issue is, we would love to use grams to measure the mass of a single atom. But that would be impossible because an atom has very, very, very small mass. So we cannot use a gram for the measurement of an atom. So they had to create a new unit that they could use. So that unit is called an atomic mass unit. One atomic mass unit is equal to 1.66054 times 10 to the power negative 24 grams. So you can see it's really tiny. It's a very small mass. This mass is usually given based on a standard. That is, the standard is carbon 12. But we are not going to focus on that. We just need to know that one atomic mass unit is this value in grams. Now, the standard that we use to measure atomic mass units is carbon, and carbon has 12 atomic mass units. So to get a single atomic mass unit, you need to divide the mass units for carbon by 12. If you do that, you get one atomic mass unit. That's what we are saying here. Now, when you look at periodic tables, you will see that the masses that we have on the periodic tables, most of them are not exact masses. And you look at why don't we have exact masses on the periodic table? Or why don't we have exact mass, atomic mass units on a periodic table? That question is answered by isotopes. What are these isotopes? I will say that isotopes are atoms that have the same atomic number but different mass numbers. So they have the same atomic number, that is, they have the same number of atoms, because number of atoms is the identity of that atom. So they have the same number of atoms, but they have different masses because they have different neutrons. So in other words, they have different number of neutrons, yet they have the same number of protons. So here we are looking at carbon. Carbon, as shown here, we are showing three stable isotopes of carbon. We have carbon 12, which has 6 protons and 6 neutrons to give us the mass number of 12. We have carbon 13, which has 6 protons and 7 neutrons to give us the mass number 13. Then we have carbon 14. This carbon is radioactive, which has 6 protons and 8 neutrons to give us mass number 14, and we call it carbon 14. Actually, you can show this using the AZX diagrams. So let me just draw the diagrams for these isotopes. So this one, the carbon 12, has an isotope C12,6. The carbon 13, let me just erase this part. So the carbon 13 has 13,6C. The carbon 14. So you can see that in all cases, the atomic number is the same. The only difference is the mass number. That's how we present isotopes. But then we have As I already indicated, on the periodic table, you don't have exact masses of isotopes. There is a reason for that. For example, if we take magnesium, which has a symbol Mg. Magnesium occurs in nature in three isotopic forms. So these isotopic forms, each of the isotopic form has what we call isotopic mass. Magnesium 24 is the most abundant one. It is found in 78.7% of the Earth. Magnesium 26 is 11% of the Earth. Magnesium 25 is 10% abundance on Earth. So whatever we have here are what we call isotopic masses for each isotope. So the question is, calculate the atomic mass of magnesium from the information that you have been given. Now, for you to do this, first of all, you need to change the percentages to ratios. So 78% becomes 0.7870%. So I'll say the actual mass ratio of magnesium 24 is 0.7870. So that is the percentage. Now I've changed the percentage to ratio. Times the mass that I'm given here, 23.985. That is for magnesium 24. For magnesium 26, 0.1117. So I'll say AMU. 0.117 times 25,983 AMU. For magnesium 25, 0.1013 times 24.986 AMU. So now what do you do? Once you multiply each mass, so once we multiply each of these masses by their ratio, you add the answers to get your new mass. So what I'm saying is, for this one, the solution is really simple. You just multiply this one, the mass, the first mass times its ratio, plus the second mass times its ratio, plus the third mass times its ratio. So 0.7870 times 23.985 plus 0.1117 times 25.983 plus 0.1013 times 24.986. All this is given in atomic mass unit. And for this one, the answer is 24.313 atomic mass unit. So that is the average atomic mass of magnesium. Only that we don't call it average atomic mass, we just say atomic mass. So there must be a difference between isotopic mass and atomic mass. Isotopic mass is for a single isotope. Atomic mass is the weighted average of all the, I'll just say, plausible isotopes that will make sense in the calculation. So we need to know, if I give you the isotopes and I give you the percentages, you just multiply each isotope by its percentage and then add them. Please do not divide by 3. In these types of problems, don't divide, you just add. Let's look at another problem. So we have natural samples of copper that contain 2 isotopes. So we have the 2 isotopes. The first one is 63 copper, which has a mass of 62.93. And then we have the second one, 65 copper, which has a mass of 64.93 atomic mass unit. And we are given the percent abundance of copper 63. So this is the percent abundance. Calculate the atomic mass of copper. So what we are looking for is to get that average mass of copper. Now, to solve this, we first need to get the percentages. So we are saying copper. I'll just say copper 63. Its percentage is 69.09%, which means the remaining copper, you just subtract 100 minus 69.09. Copper 65 has a percentage of 30.91%. So how do we get 30.91? It's just 100 minus 69.09%. So we just need to take note of that. Now we have the percentages. Each percentage has its mass. Copper 63 has a mass of 62.93 atomic mass unit. Copper 61 or 65 has a mass of 64.93 atomic mass unit. which means the atomic mass should be calculated by just getting the ratios of each percentage. So here we start 0.6909 times 62.93 plus 0.3091 times 64.93 atomic mass unit. After the calculation, we find that the atomic mass of copper is 63.55 atomic, I just say AMU, which is atomic mass unit. Atomic mass unit. So you can compare that mass with the one on the periodic table. Let me also just look at another problem. Or what I'm gonna do is that you can practice using this problem because it is similar to just the last one. The only difference is that here I have asked you to identify the element on the periodic table. So I am going to solve this problem. So quickly, this percentage goes with this one. So if this is 60.4%, the rest, which is 39.6%, goes with this atomic mass. So I'll say atomic mass of this atom is 0.604 times, that is the ratio from here, times this mass, 68.93 atomic mass unit, plus 0.396 ratio from here times this mass, times 70.92 atomic mass unit, which gives us 69.7 atomic mass unit. So the next question is identify the element. If you go on the periodic table, the element with atomic number 69.7 atomic mass units is gallium, which has a symbol Ga. So that's how we use this information. Now, let's look at something more complicated, a little bit more complicated. We have two naturally occurring isotopes of chlorine. So we have 35 chlorine shown here with a mass of 34.97. Then we have 37 chlorine with a mass of 36.97. So we are given isotopic masses. Also, we are given one more information. We are also given the weighted or the average atomic mass. We are given that, and this mass is here. So the question is, calculate the percent abundance of each of the two chlorine isotopes. Your answer to three significant figures. How do we deal with this problem? So for this one, the first thing you need to do is to use letters for the percentages. So I'll say let the ratio of Cl35 be x. So this should be a ratio, not ration. So let the ratio of Cl35 be x. Let the ratio of Cl37 be y. So these are two ratios. If you combine the two ratios, then x plus y is equal to 1. Because if I add all the ratios, they give me 1 as the answer. So I want to make this one look good. So then x plus y is equal to 1. But what am I saying? I am saying the ratio x goes with 34.97 and the ratio y, goes with 36.97. I can say that atomic mass is given by 34.97 times the ratio x plus 36.97 times the ratio y. And this gives us 35.46 atomic mass unit. Why am I doing this? It's compared to this. You can see here the ratio times mass plus ratio times mass gives the atomic mass. The same thing here. Ratio mass times ratio plus mass times ratio gives us atomic mass. So we need to take note of that. And we have our equation there. We call it simultaneous equation. Now, this is equation A. This is equation B. But if we take equation A, this equation can imply that x is equal to y minus is equal to 1 minus y. Or I can just say here x is equal to y 1 minus y, which is kind of equation C. Now what do I do? Wherever there is x, so if I write 34.97x plus 36.97y is equal to 35.46. Wherever there is this x, I replace it with 1 minus y, so that I am dealing with a single unknown. I'm not dealing with two unknowns. So I'll say 34.97. Instead of x, I put 1 minus y plus 36.97 y is equal to 35.46. Then I remove parentheses. 34.97 minus 34.97y plus 36.97y is equal to 35.46. Now I'll just erase up here to create more space and continue this problem. So I have more space here. I'll just continue the problem up there. So coming from here, going up, I'll just write this one again. 34.97 minus 34.97y plus 36.97y is equal to 35.46. Then what I do, I group the y's together, and I group the numbers without any letter together on one side. So what do I have? 36.97y minus 34.97y is equal to, if I transfer this one to this side, it will have a negative. So it's equal to 35.46 minus 34.97, which means 2y is equal to 0.49. Therefore, y is equal to 0.245, which really is 24.5%. So the question is, what is Y? Y corresponds with Cl 37. It corresponds with chlorine 37. So what this tells us is that there is 24.5% of chlorine 37. So I will say that chlorine 37, we have 24.5%. Chlorine 35, we have the rest. So 100 minus 24.5%, which is 75.5%. In that case, we have calculated the isotopes of chlorine. When given the mass, the isotopic masses, and the atomic mass. Let's see if we can solve the last problem on this side. So we have europium 151, which has a mass of 150.92. We have europium 153, which has a mass of 152.92. And this one is the atomic mass, the weighted average of europium. Now, what is the percentage of each of the two isotopes? So we do the same thing. So I'll say for this one, the ratio for this will be X, ratio for this will be Y. So I'll just say 152 or 150.92 X plus 152.92 Y is equal to 151.96. And then I'll say X plus 1 Y is equal to 1, which means X is equal to 1 minus Y. So I just do the same thing. Wherever there is X, I put a Y. So it will be, I put 1 minus Y. So it will be 150, 92, 1 minus Y plus 152, 92Y is equal to 151.96. So I remove the parentheses, 150.92 minus 150.92y plus 152.92y is equal to 151.96. I put the y's together. 152.92y minus 150.92y is equal to, I move this one to this side, it becomes a negative 151 minus 9 or 0.96 minus 150.92. So here it will be 2y is equal to 1.04. So just let me just do the calculation again. Yeah, 1.04. So I'll complete it this side, which means y is equal to 0.52, or we say 52%. So what is our y? Y is EU 153. So here we can say EU 153 is present with an abundance of 52%. EU 151 therefore is present with an abundance of 48%. When you add the two percentages, should give you 100%. Thank you. Just make sure that you complete the assignment that came with this video. Thank you.